So hello students, welcome again to my YouTube channel, and in today's video we're going to discuss about the domains theory. So first of all, before we start, we need to know a property about magnets. So let's say, for example, we have a magnet like this. Then this side is the south pole, this side is the north pole. What do you think will happen if we cut this magnet into two? So what normally happens is that, let us draw that diagram. So what normally happens is that this magnet will retain its magnetism even after cutting it into two from this part. Thereby this side becomes the south pole, this side becomes the north pole, this side becomes the north pole, this side becomes the south pole. The same will happen also if you cut this magnet into two like this. If you cut these two magnets into two, the same thing will happen. It will be like this. So this side will become the south pole, this one will become the north pole, this one will become the north pole, here will be south, and then this one will be south, this one will be north, this one will be north, this one will be south. So it doesn't matter how many times you cut the magnet, it will never lose its magnetism. The magnetism will always be retained, and each part of the magnet will retain its polarity. So this domain theory basically it talks about this phenomenon whereby whenever you break a magnet into smaller pieces. So when a bar magnet is broken into two or more pieces, the pieces retain their magnetism, each having a north pole and a south pole at its end. Each having a north pole and south pole at its end. So that is all about domains theory, which basically is just telling you that whenever you break a magnet or whenever you cut a magnet, the magnet will retain its magnetism. Each pole retaining its magnetism, having both north pole and south. So if you break it, it will also have a south pole and a north pole. So that is all about domains theory. It basically talks about that. Now we have another thing that is known as the magnetic domains. So magnetic domains, these are basically small magnetic groups. So one common characteristics of this magnetic domain is that they have a common magnetic axis, one being north pole and the other being the south pole. So let's say, for example, this magnet here, we can break it into some parts, let's say like this. So we can assume that this part here is the magnetic domains. So these are just small magnetic groups. This one is also the magnetic domain. This one is also a magnetic domain. So what happens is that whenever you break this magnet into two, what you basically will do is that you leave part of this magnet. Let's say this side will have its own magnetic domains, and this side will have its own magnetic domains. So and remember we said that one property of these magnetic domains is that they have a common magnetic axis, one being north and other being south. So even if you break this, you haven't destroyed the magnetic domains. So these magnetic domains will still retain their position. Even this one, when you broke it into two, you can just draw a sketch like this. So these magnetic groups will still be retained, whereby this half will still have its magnetic domain and this half will still have its own magnetic domain. So it doesn't matter how many times you break this, at the end of the day each part will still have a magnetic domain, which will in turn retain the magnetism of the magnet. So that explains why whenever you break a magnet into half, magnetism is retained in each half that you've just made because of the domains. And we've said that the characteristics of this magnetic domain is that they have a common magnetic axis. So by common, it means that it does not change. If you look keenly, this one was the south pole, so this one will still be the south pole and this one will still be the south pole. What will change is the position where you break it. So if you break it here, then you will switch this part to be the north pole, this one will be the north pole, this one will be the north pole. So depending on the position where you cut it, it will switch polarity at that point, because we have said that it has a common magnetic axis whereby one side becomes the north and the other side becomes the south. So another thing we need to discuss about is the dipoles. So what is the dipoles? So what are dipoles? Dipoles basically, in domains, we say that these ones are the domains, these sub magnetic groups, these are the domains. So the dipoles, domains comprises of smaller subatomic magnets. So you can say that this one are, so the dipoles are basically the smaller subatomic magnets, and they're usually found inside the magnetic domains. So we always represent them with lines like this. So you can represent with lines like that. So these lines basically represents the dipoles. So how can we be able to represent magnets and non-magnets or saturated magnets using the dipoles and the domains? So we can draw an example of a magnet here. So we start with A, which is the unmagnetized state. Now, how can you be able to represent an unmagnetized state using the magnetic domains and dipoles? So it will look like this. So we can separate this material into magnetic domains. So we said domains, these are smaller magnetic groups. So we separate them like this. And these are the magnetic domains. Later, we need to represent the direction of the dipoles. So if a material is non-magnetized, the dipole will not align in a common direction. So you'll find out that this dipole is facing this direction, another one is facing this direction, another one is just facing this direction. So they're just disorganized. This means that this material has not been magnetized. So this one shows that this material is in an magnetized state. Now let us look at another state. So state B will be magnetized state. So how can you be able to represent a magnetized state? So I can draw a material like this, and then we can break it into magnetic domains. So later on, we can represent the direction of these dipoles. So these ones are the dipoles. So the dipole will align in a common direction, but it will not be in a straight line. All the lines are facing in a common direction, but not parallel to each other. So as you can see, these dipoles are facing in a common direction, but they're not parallel to each other. Now, how can you be able to represent the saturated state? Now, for you to be able to represent the saturated state, let us first draw the material. We can separate the magnetic domains, and then we can indicate the direction of the dipoles. So the dipoles are supposed to be parallel to each other. So they all face in a common direction and are parallel to each other. So we normally say that the material is magnetically saturated. This means that all the domains get aligned in a specific direction and are parallel to each other. No further magnetism or magnetization can take place. This is the final stage of magnetism. So now let us look at this subtopic, magnetization of magnetic material. So what do you understand by this topic? Basically is the process of making a magnet from a magnetic material. So if you have a magnetic material, you can make it into a magnet by conducting a number of processes. So these processes are referred to as magnetization of magnetic material. So we have four methods of magnetizing magnetic material. So one, we have the induction method. Two, we have stroking. Three, we have hammering. And four, we have electrical method. So these three are the common methods of magnetizing a magnetic material. So let us discuss them all one by one. So first of all, we will start with the induction method. So what is induction method? What do you understand by induction method? So let us say, for example, you have a magnet. This is your magnet here. And then this part is the south pole. And this part is the north pole. So, and then let's say you have pins. You bring a pin and then stick it at this part here. So what will happen is that this pin will become magnetized. So what do you think will be the polarity of this pin if we put it like this? So the polarity of this pin will be, because this is the north pole, then this part will be the south pole, and then this part will be the north pole. So if you add another pin down here like this, then this pin, the downer pin, this part will be the south pole and this part will be the north pole. So through this process we have been able to magnetize these pins. So this method is known as the induction method. So to prove the polarity of this magnet, you can do this. And then let us say, for example, this is the north pole and this is the south pole. So you can draw the pin down here like this. So you'll realize that there will be repulsion between these two pins. Why do you think that is happening? So the reason why there will be repulsion is because, remember, this one is the south pole. So this part here of the pin will be the north pole. This part will be the north pole. And this here down here will be the south pole. This will be the south pole. And remember, we said that like poles repel each other and unlike poles attract each other. And because this is the south and this is the south pole, then the repulsion will occur here between these two pins. What do you think will happen if you bring a magnet, and this part being the south pole and this part being the north pole? What do you think will happen if you bring this magnet towards this part here? Now remember, this is south and this is south and this is south. All these are like poles. So what will happen is that this repulsion will become even more, because unlike poles repel each other and like poles attract each other. So this is the simplest way on how you can prove the polarity of these pins. So in simple terms, you're supposed to say that the end of the pins attracted to the magnet, so this part here, the end of the pins attracted to the magnet, acquires a polarity that is opposite to that pole of the magnet. So this pole is the south pole. So at this part here, where the pin meets the magnet, it acquires an opposite polarity, which is the north, which is opposite to the polarity of the magnet to which it is attached to. And also you can say that the lower end of the pin acquires a polarity similar to the pole used. For example, this is the lower part. The lower part will be now the south pole. So this south pole will acquire the same polarity to which the pole of the magnet was attached to. Even to this example, you can see we have used the north pole. So the lower pin will receive the same polarity as the part to which the pins has been attached to. So this lower part will be also the north pole. So that is a shortcut or a shorter way of knowing the polarities of these pins. So now that is all about induction method. Now let us look at the second method, which is the stroking method. So what is stroking method? Stroking method is whereby you stroke a magnetic material. So let's say, for example, you have a magnet like this. Then let's say this is the north pole, and then this part is the south pole. And then down here you have a pin like this. So this is your needle. You can call it a steel needle. Now during stroking, what you're supposed to do, you're supposed to rub this magnet. So let us say, for example, in this case, we rub this magnet toward this direction, like this. So we are rubbing this magnet along this steel needle. So what do you think will happen? So we always say that the observation made is that the needle aligns itself with the magnetic axis of the earth, whereby one of its end is repelled by the plotting compass. So if you put a plotting compass from one end of this needle, then it will deflect the plotting compass. So the fact that it repels the magnetic compass, basically it says that this needle has actually been magnetized. Now what do you think will be the polarity of this needle? So we have, let's say, call this point A, and let us call it point B. So what do you think will be the polarity of point B? So the polarity of point B will become the south pole. So B becomes the south pole and A becomes the north pole. So we always say that the end of the needle where the magnet finishes stroking, so the end of the needle, this part where the magnet, this magnet here, finishes stroking, it acquires an opposite polarity to that of the stroking end. So if you look at this one is the north pole. So the end of the needle will acquire an opposite polarity to which the stroking magnet has been used. So if this one is the north, then this part will be the south, and that's why we have said that B becomes the south pole of this magnetized material, and this part here, this A part, becomes the north pole. The disadvantage of using this method is that it produces magnets in which one pole is near to the end of the magnetized material than the other. One side, the pole will be nearer to the end than the other. For example, you can say that this part becomes the south pole, but now the north pole will not be to the farthest end. The north pole can be around here. So it produces magnets in which one side of the magnet of the poles is farther to the end than the other. So normally what we can do to counter target that disadvantage is by using the double stroke method. So what is the double stroke method? We can draw a diagram of a double stroke method. So let us say we have like a steel rod. So this is a steel rod. Now remember, we are now using the double stroke method. So in a double stroke method, what we will do is we will use two magnets. So this will be magnet 1, and then this one will be magnet 2. So what we normally do is we stroke. Let us start with this magnet. So this magnet should have opposite polarity. So if you use this one as the south pole, then this one you should use as the north pole. So we should stroke this first magnet in this direction, and this other one we should stroke it in the opposite direction like that. So remember, we said that the farthest end of the steel rod will always acquire a polarity opposite to the polarity of the magnet, the side of the magnet that has been used. So for example, here we have used the north pole. So at the farthest end where it finishes stroking, it will acquire an opposite polarity. So here will be the south pole, and here we have used the south pole. So the farthest end will require an opposite polarity of the north pole. So here we have been able to counter target the disadvantage of this, whereby we said one of the polarity is farthest to the end than the other. So here all of the polarities will be on the farthest end. So this one will be the north pole, and this one will be the south pole of the magnet. And this method is known as the double stroke method. Now what do you think will happen if you use the same polarities here? Now, let us say for example, let me clear this. Let's say for example, what do you think will happen if we change the polarities of this magnet? We use the same polarities, this one becoming the north pole, this one becoming the north pole, this one becoming the south pole, and this one becoming the south pole. So I remember we said that at the end of the bar, or at the end of the stroke, it will acquire a polarity that is opposite to the polarity of the side used in stroking. So if this is the north pole, then definitely this part will be the south pole, and if this is the north pole, then definitely this will be the south pole. Now remember, this part where you start stroking will become the north pole, and this one will become the north pole. So this is the polarity of the magnet if you interchange and use the same polarity of the magnet during stroking. So you will have a magnet that looks like this. So this is a magnet with a consequent poles at the center, whereby this part is the north pole and this part is the south pole. So we have the same polarity at the middle. So the most important thing you need to know is that at the end of stroking, it will acquire a polarity that is opposite to the pole used by the magnet during stroking. So this one is the north pole. So definitely at the end of stroking, this part here will be the south pole. So up to this point, we have looked at induction method. We've also looked at stroking method. Now let us look at hammering method. So how do we magnetize a material in this method? Now let us say for example, you have a steel bar like this, then you have your hammer here. So this is your hammer. So how can you be able to magnetize this steel bar by hammering method? What you're supposed to do is that you're supposed to align this magnet in the Earth's magnetic field. So we are supposed to align it like this. Let's say this is the Earth's magnetic field. So this being the north pole and this being the south pole. So you're supposed to align it parallel to the Earth's magnetic field, and then one end of the bar magnet should be hammered by this hammer, you hit one end. So when you hit it, this steel bar will get magnetized, and that is the simplest method of magnetizing a magnet using hammering method. You just have to align. Remember, it is very important to align this steel bar with the Earth's magnetic field. So you need to align it. You need to place it in a north-south direction to be parallel with the Earth's magnetic field, and then you're supposed to hammer one side of the steel bar, and then this steel bar will become magnetized. So now let us look at the last part of method of magnetizing magnetic material, which is the electrical method. So how are you supposed to magnetize magnetic material using an electrical material? So you can use a solenoid. So for those who do not know what a solenoid is, so a solenoid basically looks like this. It's just a winding around, let's say, a tube-like thing. You can have something like this. So remember, here there's an entrance. There's a space in between. You can enter something inside here. So, and then what normally you're supposed to do is you're supposed to wind a wire around it like this. So here you can have a variable resistor to control the amount of current flowing in the circuit. So down here you can have a battery. So you can choose to have a switch here. Let us have a switch here. This is a switch. You can open or close the circuit. Now let us call this part A, this part B. So what you can do is, let's say for example you have a steel bar. What you can do is you need to enter your steel bar inside here, this part. So this is our steel bar, like this. So when you close this circuit, current will flow through this path, and then this steel bar will get magnetized. Now how can you be able to know the North Pole and the South Pole from this method? For you to be able to know the North Pole and South Pole of this method, it will only depend on the direction of the current flowing in the circuit. So the direction of current, if it flows in this direction, then the polarity will be different than when the current flows from this direction. So we have two methods of identifying the polarity of this magnet. So one of the methods of identifying the polarity of this magnet, we have the clock rule, and two, we have the right hand grip rule. So in physics, make sure you take note of the hand that you're supposed to use. So if it's the right hand, you're supposed to use the right hand. If it's the left hand, you're supposed to use the left hand. That is very important, because if you switch the hands, then you will get a different answer. So it will be much more easier if you use the clock rule, if you do not master the right hand grip rule. But if you master them both, then well and good. Now how can we be able to know the polarity of this magnet using the clock rule? So the clock rule usually states that if one is viewing one end of a bar, let us say for example you are viewing this end of a bar, if the current flows in the clockwise direction, let me just differentiate between clockwise and anti-clockwise direction. So if this is a wall clock, we all know that the minute hand is always longer than the hour hand, and these hands usually flows in this direction, because they usually move in this direction. So if this is the minute hand, it will keep on moving in this direction. So this direction represents the clockwise direction. Let us say current, in this case current is moving in this direction and your eyes is facing this part here. So if you represent this, you'll see that this is flowing in this direction. It's flowing in this direction. So do you think that is clockwise or anti-clockwise? Now if you look keenly, you realize that it is flowing in this direction, because your eyes are facing this way. So it is flowing opposite clockwise direction. So that means that this one is not in clockwise direction. But if it was to be in clockwise direction, then it means that the polarity at that part would be the south pole. The polarity of that part is the south pole. So the clock rule states that if one is viewing one end of the bar, the current flows in clockwise direction, then that end is the south pole. So if it is flowing in a clockwise direction, then that end is the south pole. And if it is in anti-clockwise, then that end is the north pole. So the best formula to use is this. You can just draw something like this. So this one represents the N, and then you can draw it like that. So the north pole is in anti-clockwise direction, and the south pole will be in clockwise direction. So this is flowing in this direction. So if it is in clockwise direction, then it is the south pole, and if it is in the anti-clockwise direction, then that is the north pole. So I think this is the best formula to use when it comes to the clock rule. You can just draw the north like this and south like this, and then the farthest end you put the pointers. So this one indicates the direction of flow of current. So if it is in the clockwise, then it is the south pole. If it is in the anti-clockwise, then that is the north pole. So that is all about the clock rule. Now let us look at the right hand grip rule. How can you be able to identify the polarity of this bar magnet using electrical method in right hand grip rule? Now something that I forgot is that, remember, whenever you are trying to magnetize a magnetic material in electrical method, you're supposed to use a direct current, not AC. Okay, so if you're trying to magnetize it, you're supposed to use a direct current. Now let us look at how you're supposed to know the polarity of this iron bar using the right hand grip rule. So you can remove this. So how can you be able to identify the polarity of this by using the right hand grip rule? So let's say, for example, this is the solenoid and the current is flowing in this direction like this. So what you're supposed to do is you're supposed to grip this solenoid using your right hand. So I can just draw a sketch on how you're supposed to grip. So you grip it whereby the thumb should lay like this, and then your other finger should now grab from top like this. So when you grip it like this, so what we normally say is that if a coil carrying current is grabbed in the right hand such that the finger points to the direction of current in the coil, then the thumb points to the direction of the north pole. So if you grab this solenoid like this, whereby these fingers are now pointing to the direction of flow of current. Remember, this current is flowing in this direction. It's flowing in the upper direction like this. So these fingers are pointing to the direction of flow of current like that. So it means that the thumb will point to the north pole of the induced magnet. So we remember here in the middle we have our steel bar like this. So this one will be the north pole and this one will be the south pole. So this one is the easiest method of identifying the polarity of a magnet, whereby if you grab it with your right hand, then your thumb will always point to the north pole of the magnet. And that is all about methods of magnetizing a magnet. Now, having done discussing on methods of magnetizing a magnetic material, so how can you be able to demagnetize this magnetized material? So let me clear this. So we can look at demagnetization. So now let us look at methods of demagnetizing a magnet. So we have a number of methods of demagnetizing a magnet. So one of the method of demagnetizing a magnet is using the hammering method, and two is using the electrical method. Now I want you to take note that these two methods are similar to the methods of magnetizing a magnet, but now the process is different. So let us start with the first one, which is the hammering method. during magnetization, what we used to do is we used to align this magnet like this. You align it with the Earth's magnetic field. Let's say this is the Earth magnetic field, this is the North Pole, and this is the South Pole. So let's say this one is the magnetic material. Let's say it is a steel bar. So what we used to do is we take a hammer. Let's say this one is your hammer, and then you're supposed to hammer this part. While this is aligned in the north side direction, which is the Earth's magnetic field. Now, during demagnetization, what you just need to do is to align it opposite to the magnetic field of the Earth. In demagnetization, what you should do is you align this magnet like this, east-west direction. Let's say this is the Earth's magnetic field, this is the North Pole, and this is the South Pole. So you're supposed to align your magnetized material like this, so it is perpendicular to the Earth's magnetic field, and then you're supposed to hammer this part here. So what basically you'll be doing here, you'll be demagnetizing this magnet. So this is one of the method of demagnetizing a magnet. Now this next method of demagnetizing a magnet is using the electrical method. So how can you demagnetize a magnet using electrical method? Now for electrical method, remember in magnetization, during magnetization process, what we used to do is to use a DC. So we were using a DC current or voltage. So it's a direct current. Let's say you can use a dry cell batteries to magnetize this material. But for demagnetization, here we will use an alternating current. So for instance, we can have a solenoid like this. So you need to power up this solenoid with a alternating voltage or alternating current, the same thing. So this is, let's say we use 12 volts alternating. So we always represent alternating with this. So this one is AC. So what will happen is you need to align this in the east-west line. So it is kind of similar with this. So this one should be aligned in the east-west direction. Let's say this one is the east-west direction. Now remember here in the middle we have a steel rod. So this is our steel rod. This is the material that we are trying to demagnetize. So originally right now it is magnetized, so we are trying to demagnetize it. So we need to align it in the east-west direction and then pass alternating current of 12 volts around the solenoid. So what will happen is that the dipoles will get disoriented. That is the best explanation to give to explain how demagnetization occurs. So we always say that the dipoles get disoriented, whereby it changes the direction of these dipoles. They just disorient. They start looking in different directions. I remember we drew representation of magnets in saturation state, a material in magnetized state, and materials in non-magnetized state. So in non-magnetized state, we say that the dipoles always face in a different direction. In saturated state, we say that the dipoles face in, they are parallel to each other and they face a common direction. And in a magnetized state, the dipoles face a common direction, but they are not parallel to each other. So in this case, when you place your solenoid having the magnetized material inside and then you pass alternating current inside and it is in the east-west direction, so what will happen is that the dipoles will get disoriented, hence you'll be demagnetizing this material here inside. These two methods are the methods that can be used to demagnetize material. So you're supposed to take note of the direction you're supposed to use. For during hammering, you're supposed to place your steel bar in east-west direction, and also in electrical method you're supposed to direct your steel bar in the east-west direction so that it does not align with the Earth's magnetic field. And in this process, you'll be disorienting the dipoles, hence demagnetizing the magnet. Now, one thing that you need to know about alternating current is that it keeps on alternating, like the current reverses in direction. So it keeps on reversing many times per second. I think you know about alternating current. Alternating current, let's say for example, this is an electron here. It will keep on shifting direction from one side to another. because even if you look at the direction of the graph of alternating current is a suicidal. So it's like a sine wave, whereby the current keeps on changing direction. So it keeps on changing direction now and then. So if this is an electron at this point, it will keep on shifting direction from this side to this side. We always use a 50 hertz frequency, so it keeps on switching direction 50 times per second. So this reverse back and forth change many times per second is what causes the disorientation of the magnetic dipoles. So the shifting direction of alternating current causes the dipoles to disorient. So that's why during demagnetization we normally use alternating current, and during magnetization we use direct current, because direct current just follows a common path. So a direct current will just follow a common path, it will just flow in a straight line, but alternating current will keep on shifting direction. Now a common question you might ask is, why do we have to align this solenoid in a east-west direction during demagnetization using alternating current? So the reason why we align it in east and west direction is so that this material, this steel bar inside here, so this is a steel bar, so is for this steel bar not to retain some magnetism due to the Earth's magnetic field. Because remember, if you align it with the Earth's magnetic field, let us say for example you do this experiment and then you align it with the Earth's magnetic field, which is the north and south direction. So what will happen is that some magnetic field will be induced inside this steel bar due to the Earth's magnetic field. So that's why we try to disalign it with the Earth's magnetic field. So it's supposed to be in the east-west direction for it not to retain some magnetism during the process. Now, having discussed about methods of magnetizing and demagnetizing magnets, next we need to look at the difference between hard and soft magnets. So we have two types of magnets. So we have hard and soft magnets. So what is the difference between these two? What is a hard magnet and what is a soft magnet? So a soft magnet, this one, so these are magnetic materials that get magnetized easily. So these are materials that get magnetized easily. Also, they do not retain their magnetism. They do not retain their magnetism. So you can give an example of one of the properties of a soft magnet is that one, they get magnetized easily. So it is very easy to magnetize this material. And two, they do not retain their magnetism. The application of this soft iron magnetic material, they can be used to make electromagnets. They can also be used to make transformer cores. They can also be used to make magnetic shields. So these are some of the application of soft iron magnets, and a very good example of this soft iron magnet is a soft iron armature. So soft iron armature is a very good example of a soft magnet. So a hard magnet, these are materials that they are very difficult to magnetize. Another property of this hard magnet is that it retains magnetism. So these hard magnets usually retain magnetism. So remember, these are two parts. So hard magnets, it's hard to magnetize this material, and at the same time, once they are magnetized, it retains its magnetism. So a very good example of a hard magnet is a steel. So an example, we have a steel. So it's very hard to magnetize a steel metal, but once it gets magnetized, it retains its magnetism. So that is the main difference between hard magnets and soft magnets. So hard magnetic material, it's hard to magnetize them, but they retain their magnetism once magnetized. A soft magnetic material, they are easily magnetized, and at the same time they do not retain their magnetism. So that is all about hard and soft magnets. Now the next part we are supposed to discuss about is storing magnets. So why do we need to store magnets? There is something that is known as self-demagnetization. So self-demagnetization is whereby with time these magnets tend to lose their magnetism. So with time the strength of these magnets tends to weaken. So magnets tend to become weaker with time. So we need to store these magnets so that it retains its strength. So to prevent this from occurring, what we normally do is we use steel. Then at this part we have the second steel. So we normally are supposed to store these magnets in pairs like this. So you can have the first magnet on top and the second magnet on the bottom. So this one is like this. Now if this is the north pole and this is the south pole of the magnet, then this one is supposed to be the north pole. So we're supposed to align this to be the north pole, and this one should be the south pole of the magnet, of the other magnet. Remember, this is steel. So what will happen is that at this part here will become south, this part will become north, this part here will become north, this part here will become south. So the polarities keep on changing when you attach a magnet. I think we discussed this previously. So I need you to take note that this thing here, this one, is referred to as the keeper. They refer to as the keeper. They are the ones that are used to retain the magnetism of this magnet. Now, how does it actually retain magnetism of this magnet? So we always say that the dipoles in the magnet and the keeper forms a complete loop. For instance, we all know that the magnetic loop, we all know that they originate from north to south. So it forms a complete loop whereby this north goes to south, this north goes to south, this north goes to south, and this north goes to south. So it forms a complete loop. Here, no magnetism will be lost. So these keepers have been used to create a complete loop of these magnetic dipoles. Remember, the dipoles are just the direction to which the domains are facing. Let's say if you have a domain, then the dipole will be facing at a given direction. So this direction will be common and it will form a complete loop. And in this process, then the magnetism will be retained even with time. So with time, there will be no self-demagnetization. So this is a method of retaining magnetism. So I hope you've understood the topic. This is all about magnetism. This is all about this topic called magnets. And if you have a question, just drop it in the comments below and I'll sure enough answer your questions. So until next time, bye bye.